Hi there, this is your favorite non-Indian math channel, and in this video I'm going to introduce you a very important theorem to calculate limits of sequences, and in the end we will also have an example. And I'm going to prove this theorem for the first case. So we basically have two cases. Our initial goal, our goal is to calculate this limit as n goes to infinity, an over bn. So we have two cases, like in the normal limits. If both of them goes to 0, and we also have an extra condition, bn is decreasing, or if bn goes to infinity and it's increasing. So it's like 0 over 0 and infinity over infinity. And if you remember from functions, we had L'Hopital's rule. And here it's almost exactly the same, and we have discrete L'Hopital's rule, and I will also explain this a bit. What does this delta mean? And so this means that if we have this limit of an plus 1 minus an over bn plus 1 minus bn, if this limit exists, let's say if this is equal to a, then this limit is equal to a. So it's really important. And so let's first talk about this delta. So normally when we are defining derivatives, we say f prime x is equal to limit. So we have an increment as h goes to 0, we say f of x plus h minus fx over h. And so this is for functions, and if we have sequences, we can't really pick any h for increment. Like, so if we say an, we can say a of n plus 1 over 2. Like, it doesn't make sense. You can pick h being equal to not integer, okay? And it has to be a positive integer. So we can pick h being equal to 1. So what would happen if we pick h is equal to 1? So I would have f of x plus 1 minus fx over 1, h is 1, so I'm not going to write that, and there is no discontinuity. So this is just equal to this thing, and we define this thing as delta f, or we can say delta fx. And this is called discrete derivative, and there's a whole whole area of calculus that dedicated to that. It's all starting from this thing, and they're really cool stuff. I will also make videos about it. So yeah, this thing exists, and it's called, yeah, we can call it like finite calculus or calculus of finite differences. So let's go to our proof. So my goal, I'm going to prove the first case, and so I'm going to say if this limit exists, I'm going to say it's equal to a. I'm going to use these conditions, an goes to 0 and bn goes to 0 and it's decreasing. And in the end, I'm going to prove that limit of an over bn is equal to 0, okay? So let's see. So first, if I know that this limit exists, where limits of an plus 1 minus an over bn plus 1 minus bn, if this is equal to a, what can I say by the definition of limits? I can say for each epsilon, there exists an n, which is an integer, such that, so this thing, sorry, it's just bn plus 1, and so my limit is a minus a, this is going to be less than epsilon. So this is going to be true when n is greater or equal than this capital N. And so this is by the definition. And I also know that, let's also note this stuff, that an goes to 0, and bn is going to 0. And I know that bn is decreasing. So bn plus 1 minus bn is, so this is going to be positive. And I also know that since this thing is decreasing and it's going to 0, so it's going to look something like this, okay? So it will always be positive. So I can also say bn is greater than 0. We are going to use this stuff, okay? And yeah, I don't want to explain them during the solution. So we have this difference being positive, bn is positive, and both of these limits are going to infinity, going to 0. Okay, so let's see. So from this thing, I want to get rid of this absolute value. What can I do? I can just say it's between minus epsilon and epsilon. Let's write it a bit more left, right. So this thing is between epsilon and minus epsilon. It's equal to that. And so I also want to get rid of this a on this step. I can add a to all sides. And so this is going to be true whenever this is true, which means that whenever we have n is greater or equal than this capital N. Okay, cool. So now, what can I do? I want to do some stuff that we will see in few more steps. So I kind of want to make this thing a bit simplified. Okay, I don't want to have something at the denominator. So let's multiply everything by bn plus 1 minus bn. And since, like I said here, this is positive, so inequality won't change signs. I have a minus epsilon Okay, cool. So this is again true just when n is greater or equal than this capital N. So what can I do? This is the main trick of this problem. And so I know that this is true for each n greater or equal than this capital N. So would this be true if I pick n being equal to n plus 1? Yes, n plus 1 is bigger than it. N plus 2 is still bigger than it. So I can actually write this for bigger n's too. So instead of n's, if I put n plus 1, this inequality will still be true, and we will see why are we doing this. So if I put n is equal to n plus 1, it's going to be bn plus 2 minus bn plus 1. We are doing the same here, an plus 1 less than epsilon plus a. So why did we do this? Basically, I want to get far from this an. I'm gonna keep doing this for a few steps, and in the end, I'm just gonna add them, because if you notice, if I just add these two lines, these two will cancel out. And if I actually do it again, these two will also cancel. And it will just keep canceling. And in the end, I will have something a bit more simple. So if I keep doing this till m, so this thing is always one less than that. So I have bm minus 1. This is same with that. So it's just am minus 1. And this is less than epsilon plus a. Again, just bm minus 1. So again, like I said, if I just add everything up, these stuff will cancel out. If I look at this side, it's going to be at the parentheses of a minus epsilon. Again, this stuff will cancel out. And also on this side, this stuff will cancel out. So what will I have is a minus epsilon. I will have only this last term and first term, bm minus bn. Which is less than am minus an. Which is less than, okay, we're almost done, bm minus bn. So I kind of got a bit further from this an. I got m minus n far, and here what can I do is that I want to take this like being far from an to infinity. Okay, we will see what does it mean. So my goal was to get limit of an over bn. So I want to squeeze this thing, or this is equivalent to squeezing am over bm, because if I squeeze this, it's squeezing this thing, and limit of an over bn is of course equal to limit of am over bm. And here I could actually do both, but I would need to swap this m and n, or I could just deal with negatives. We have few options. So what we can do is we can just divide all sides by bm, and we will get am over bm. Okay, so again, bm is positive because bn's were positive, so it's going to be 1 minus bn over bm. So I'm dividing all sides by bm. And now, so I want to use that limit of an and bn is going to infinity. But here, if I take limit of n goes to infinity, well, it will be good. If I take m goes to infinity, why it's wrong? Because I have m's at the denominator, and bm's will gonna go to 0, and I will have something over 0, which will be undefined, and I don't want that, okay? And what can I do is just take this n goes to infinity, okay? So if I take limit of n goes to infinity, what will I get? So here, if you look, m is just a number, okay? So bm is also a number. It's not infinity. It's not any close to infinity. So if I take this limit as n goes to infinity, this is going to be equal to limit of bn over limit of bm. And limit of bm is just going to be equal to bm. And limit of bn is going to be 0 because bn goes to 0. So this thing will just be 0. So what can I say is that a minus epsilon, this thing will just go to 1. 1 minus 0, which is 1, less than. So I don't know what is this limit, but I can write it directly because this is like a constant for n. So limit of n goes to infinity am over bm is still same, okay? There is no n in it. bm less than. So again, this is exactly the same logic. an over bm, bm is a number, n goes to infinity, this limit will be 0, less than epsilon plus a, and this thing is exactly the same with that one, so it's gonna be just 1. So what did I get is that a minus epsilon is less than am over bm less than epsilon plus a. So this is true whenever n is going to n went to infinity. Well, I don't really care about that. What I know is that this is true. M was bigger than n. I don't know if I said that, but here I went from an plus 1, n plus 2 up to m, so m is of course bigger than n. So here, if I look what I squeezed here, instead of an over bn, I squeezed am over bn. And now if I just again subtract a's from all sides, it's gonna be true whenever minus epsilon am over bm. And so this is also, let's write it on this line. I'm gonna have am over bm minus epsilon minus a is less than this epsilon. So what does it mean? This is again just almost same with the definition of limits. And here I have some m's which are quite big because I said n goes to infinity. M's were bigger than n. So I know that whenever m's are bigger or equal than bigger than n, this will hold, and therefore, so when m's are really big, this limit of m goes to infinity, am over bm will be equal to a. And so here, instead of m's, I can just put n, because in the theorem we said we used n. An over bn will also be equal to a. And this finishes our proof, okay? So let's do one example. This is going to be a little abstract problem, but you can apply to any problem that fits. So I'm going to say, let's say limit of an is equal to 2. And so, of course, this is not the problem. So we are asked, what is limit as n goes to infinity? So I'm going to say a1, a2, up to an over n. What is this limit? So how can we find that? We have no idea about an. Well, you can do this by classic methods of squeezing stuff, but it's not going to be so short. Of course, it's going to be a bit shorter than proving this theorem, but since we know this now, we can use the theorem. So is it the first case or second case? So if you remember at the first case, I don't want to go back up, we had 0 over 0. At the second case, we had infinite over infinity. So what we can do is it fits to the second case because n would go to infinity. I don't know about this part, but this thing goes to infinity. And of course, this thing also goes to infinity because actually, I don't know that. But yeah, it should go to infinity. So what can I do is that, so I'm going to consider the sequence, okay? So I'm going to say, let this thing be, so I'm picking bn being equal to n because I have something in the form of over bn. And let's say this thing, I can say an, so let's say cn. I have something in the form of cn over bn. So how can I do this thing? By our theorem. So bn is n. It's of course increasing and it's going to infinity. And my an is going to be just this whole thing. Sorry, I'm using the letter cn. So this is a1 plus up to an. And so I'm going to consider the limit as n goes to infinity, delta cn over delta bn. So, and in the end, I'm going to say if this limit exists, it's equal to this thing, okay? It's equal to my problem. So what is delta cn? Cn plus 1 minus cn. And what is cn plus 1? Well, so I'm adding up to n, and if I add up to n plus 1, it's just going to be the same thing, except it's going to end up with an plus 1. And cn plus 1 minus cn is just going to be the last term. So limit n, this means n goes to infinity, so I have n plus 1 over, so delta bn means bn plus 1 minus bn, and this means just n plus 1 minus n, which is 1, so I have just 1. So this is equal to limit as n goes to infinity, so I have something much simpler. Sorry, not n, an plus 1. Okay, cool. So my answer, so this limit would be equal to limit of an plus 1. So what is this limit? Of course, it's equal to limit of n goes to infinity, an. Why? Well, if an is increasing, so this an plus 1 is just subsequence of it. Or I can think like I just shifted each term by 1, okay? I only didn't take the first term. So of course, if limit of an exists, it's going to be equal to limit of an plus 1, okay? So therefore, this thing is just equal to 2. And this is our answer.